Yeah, what's up? I'm Fredotson, and I'm recording this video using Microsoft PowerPoint. Hey, that's pretty cool. I don't have a cool editing software, so I just... Yeah, anyways. So, first of all, what's a function? For those of you who don't know what functions are, just wonder why we commonly use f of x to denote polynomials. For example, f of x is equal to x squared. Now, f of x is equal to x squared right here indicates that it's a function. It's to square any number fed into it. F of 1 will be 1 squared, which is 1. F of 2 will be 2 squared, which is 4. F of 15 will be 225. What do you mean by the graph of a function? Well, we know that the graph consists of two perpendicular lines called axes, namely the y-axis and the x-axis. We usually understand that in f of x is equal to x squared, f of x will be used to represent the y-axis and x, of course, the x-axis. You'll get it soon later. Now we're moving on to linear functions. This is like some simple 6th grade algebra. Suppose you have f of x is equal to x plus 1. Instead, let's move on to a cooler example. F of x is equal to 3x plus 2. Now, how do we graph that? We put down specific values for x, 3 of them, and then we find out what f of x comes out to be. For example, put in x is equal to 1, we get f of 1 is equal to 3 times 1 plus 2, which is 5. We then express it in the form of x comma f of x. When x is 1, f of x is 5, therefore 1 comma 5 is one of the points we need. Similarly, we get 2 comma 8 and 3 comma 11. Now let's plug in these points in the graph paper or Desmos if you will. So that's 1 comma 5, that's 2 comma 8, and that's 3 comma 11. Now connect these. Yep, that's the thing. Remember that the graph should come out to be a straight line. That's why it's called a linear function. Wow, I don't know why I did that. Now let's move on to polynomial functions. Now we're moving on to something that you learn to graph a lot later. The simplest way to graph a polynomial is by finding its factors. Suppose you have f of x is equal to x squared minus 2x plus 1. Its factors will be x minus 1 times x minus 1. We can say that f of x is equal to x minus 1 whole squared. Here's the things we need to plot on the graph. X-intercepts, y-intercepts, the behavior where it intersects the x-axis. Now there are 3 specific behaviors when a polynomial graph comes in contact with the x-axis. But first we've got to understand the term multiplicity. The multiplicity of a factor is just the power of it. For example, in x plus 2 times x plus 8 whole cubed, x plus 2 has a multiplicity 1 and x plus 8 has a multiplicity 3. Now here's the specific behaviors of the graphs as they touch the x-axis. Okay, so first of all, we have when the factor or the 0 on the x-axis that the graph is touching is having an odd multiplicity. So the graph basically touches the x-axis, bounces a bit, and then goes straight through. Then we have when the multiplicity is even, it just bounces, and when the multiplicity is 1, it goes straight through. Yeah. Now here's an example. X times x minus 3 whole cube times x plus 2 whole square times x minus 1. The x-intercepts are 0, 3, negative 2 and 1, and the y-intercepts is 0. And of course, here's the graph. We also take an additional point to find out where the graph begins. For example, let's take negative 3 comma something negative. Now we don't need to specify what that something negative is. We just know that it's that the y value when x is negative 3 is negative. Right, we know that by plugging negative 3 into the function. Now so let's plot in the x-intercepts and the y-intercepts and draw the graph. Yup, that's that. Let's figure things out. So to see what to see that if we are on the same page or not. So first of all, the graph begins from the negative side. We found that out by taking the additional point. And we've also found that it touches the x-axis at the points -2, 0, 1 and 3. Now when it touches the x-axis at -2, the multiplicity of the factor x plus 2 is 2, which is even. Therefore it touches the x-axis and bounces back. Then it goes towards another 0 of the polynomial, which is 0, and then it goes straight through because the multiplicity of x is 1. Then it goes back to another 0, which is 1, and the multiplicity of x minus 1 is 1, which is 1, and so it goes straight through the x-axis, and then it goes to another 0, 3, the multiplicity of x minus 3 is 3, which is odd, so therefore it just touches the x-axis, bounces a bit, and then goes straight through the x-axis. Yep, so that's why we need the multiplicities to determine the behavior of the polynomial. So yeah, now you can graph any polynomial, I guess. Now the graph in decimals is a lot stretched than this, but it's still the same shape, isn't it? Now I'll discuss how we can determine the stretchiness in another video probably. Another example is f of x is equal to x squared plus 2x plus 2. Is this factorizable? No. Therefore, see, f of x is equal to x squared plus 2x plus 1 plus 1. Now we can factorize this a bit. F of x is equal to x plus 1 whole squared plus 1. Now this is basically just the graph of x plus 1 whole squared moved 1 unit upwards. This graph has no s-intercepts. Now let's talk about exponential functions. At this time we've had x as a base for a constant power. But what if we have it as the exponent? F of x is equal to 2 to the x is an exponential function. What we need to know is that f of x can never be 0. What we need to know is that f of x can never be 0, alright. So that means y is equal to 0 is a horizontal asymptote for the graph. An asymptote is something that a graph keeps getting closer and closer to but never touches. It's an imaginary line, that's why I've showed it as a dotted line. An asymptote, okay. Now f of 1 is equal to 2, f of 2 is equal to 4 and f of 0 is equal to 1. Plug those points into the graph and then draw the general shape through those points. The general shape for an exponential function looks something like this. Alright, so that's the graph. Now let's have another one. F of x is equal to 5 minus 2 to the 3 minus x. Now this can't be 0. Therefore f of x can't be 5. The horizontal asymptote is at f of x is equal to 5. Find some more points. 3, 4, 2, 3 and 1, 1. Let's plot this one. 3, 4, 2, 3 and 1, 1. Draw the asymptote and then draw the general shape through these points. Great, that's a graph. Now we're moving on to logarithmic functions. A logarithmic function is something you call an inverse function. It's an inverse function to an exponential function. If a to the b is equal to c, then we say that log ac is equal to b. You'll get used to it. Fun fact, 2 to the log 2x is equal to x. Because 2 to the x and log 2x are inverse functions, 2 and log 2 cut each other and we are left with x. Basically, that's the behavior of inverse functions in this case. Alright, let's graph something. Log x looks like this. Log negative x looks like that. Negative log of x looks like that. And negative log of negative x looks like that. Now, we can draw a conclusion from here. Can we say that the horizontal head of the graph always heads towards the quadrant that is represented by its signs? Now what does that mean? See, the logarithm is negative and x is also negative. Therefore negative comma negative, which is the third quadrant. The graph, the horizontal head of the graph does head towards the third quadrant. That's a way we can just understand logarithmic graphs. Graphing something. Let's try graphing f of x is equal to 3 minus log 4 5 minus x. Now, can x be 5? No, because log 4 0 is not defined. Log 0 is not defined for any base. Alright? Just like an exponential function can never be 0, this also can't be 0. 5 minus x can't be 0, therefore x can't be equal to 5. Therefore we get that a vertical asymptote for this function is at x is equal to 5. Now see, 1 comma 2 is one point, 4 comma 3 is another, minus 11 comma 1 is also another, and we'll also find the vertical asymptote. We'll also plot the vertical asymptote, and then we'll draw the general shape for a logarithmic graph. Yeah, so eventually, sorry for the voice crack, I'm going through puberty, okay? So eventually the graph's horizontal head apparently cuts through the x-axis and goes towards the third quadrant, because the sign of the logarithm is negative and the sign of x is also negative. Woohoo! Now we are moving on to modulus functions. The modulus function accounts for some tricky pre-calculus questions. It's denoted by f of x is equal to modulus x. It's basically that if we put in a negative value for x, it will always pump out a positive one, and if we put in a positive value of x, it will still pump out a positive one. Here's a cool question. Modulus x minus 2 whole squared plus modulus x minus 2 is equal to 0. What we have to do is find the values of x. Alright, for this one I want you to solve the problem. Done? No? Alright, I'll wait. Done? No? Okay, I'll wait. Done? Okay. Okay, so the answer to this question is as shown. Oh yeah, also the modulus x minus 2 is equal to negative 2 is not possible, because the modulus of x minus 2, the modulus of anything is always positive. So we'll just remove that right here. And also we ended up with modulus x minus 2 is equal to 1. That makes us get two different scenarios. X minus 2 is equal to 1 and x minus 2 is equal to negative 1. We'll get the values of x from these two. Yep, that's correct. How do we graph this? The general shape for the graph of f of x is equal to modulus x is just in simple terms a v. Now graph f of x is equal to modulus x minus 2 plus 3. Just kidding. There's a trick. So basically, if you want to graph a times modulus x minus b plus c, you've just got to move the b units upwards and c units towards the right. So yeah, that's the graph for f of x. If the coefficient of the modulus is negative, then it will be an upside down v. Now we'll be talking about piecewise functions. This is when we build a function step by step. It's like a custom function, a sandbox if you will. Now, here's an example. F of x is equal to x plus 2 when x is greater than 0 and 2 to the x when x is smaller than or equal to 0. This will give us a graph that looks like this. Oh, okay. that's a hole to indicate that the graph doesn't exist at that specific point 0, 2. Now it's pretty straightforward. It's just mixing up a few graphs to get cool results. Now let's talk about the greatest integer function. I don't know why it's called the greatest integer function, because it's literally the smaller integer function. But yeah, I guess it's denoted by f of x is equal to floor of x. It has a lot of other names like floor functions, ceiling. I don't know why though. It doesn't really make sense. It basically says if you feed it any non-integer real value, it will pump out the smaller integer near it. So that basically means that the floor of negative 0.999998 is equal to negative 1, and the floor of 2.4326 is equal to 2. Do you get it? That's it. Can you graph it? Nah, I do it for you, that's why I'm here. Now here's the thing. When x is greater than or equal to 0 but smaller than 1, f of x is equal to 0. When x is more than or equal to 1 and smaller than 2, f of x is equal to 1, and so on. See, it's like step, 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 step. Yeah, it's a weird graph. These holes right there let you know that hey, x can't be that when y is that. Do you see those holes? Yeah, that's what they're there for. Now we'll talk about radical functions. Did you forget the square root of x? Yep, we haven't done that, and its graph is quite different. Root x looks like that, root negative x like that, negative root of x looks like that, and negative root of negative x looks like that. Now we'll also talk about the cube roots and the odd roots. The cube root of x looks like that. The negative cube root of negative x is the same, which looks like that. The cube root of negative x looks like that. And the negative cube root of x is the same, which looks like that. Plotted properly, these graphs actually start to make a lot more sense. Now we're moving on to my favorite graphs, the rational functions. We've seen lines, parabolas, holes, and asymptotes. Now we'll see hyperbolas. You see, rational functions are any f of x is equal to p of x divided by g of x. 1 over x is a rational function, and its graph looks like this. Weird but cool, right? As well, graphing these functions, and we'll talk about asymptotes a lot. Asymptotes are the very essence of rational functions. So we need the x-intercepts, the y-intercepts, the horizontal asymptotes, and the vertical asymptotes. Let's understand how we can find a vertical asymptote. You know how the denominator of fractions can't be 0? Yeah, so we do that. Let's start with an example. F of x is equal to 8x over 3x minus 5. Set the denominator equal to 0. We'll get the vertical asymptote as x is equal to 5 over 3. There, that's all we need to do. Then, in order to find a horizontal asymptote, we need to consider 3 different cases. 1. When the degree of the numerator is smaller than the degree of the denominator actually. The horizontal asymptote is a constant next to the thing. Example, in f of x is equal to 1 over x, it can be written as x to the 0 divided by x to the 1 plus 0. The horizontal asymptote will be 0. 2. When the degree of the numerator is the same as the degree of the denominator, the horizontal asymptote will be given by the coefficient of the highest power of x in the numerator divided by the coefficient of the highest power of x in the denominator. Yeah, so the example I've given right here is wrong. I don't know why, maybe I'm just dumb, but yeah, you get the point. Now the third case actually leads to a slope asymptote, which is when the degree of the numerator is greater than the degree of the denominator. First of all, let's try graphing f of x is equal to 8x over the 3x minus 5. Now here, where the vertical asymptote is x is equal to 5 over 3, as we've already found out. The x-intercept is at 0, the y-intercept is also at 0, and the horizontal asymptote is at y is equal to 8 over 3. Plug those in. This, and that, and then draw the graphs. This and that. Great. Now, let's move on to a more complex example. F of x is equal to 2x squared plus 6x minus 8 divided by x minus 2. It's here that the degree of the numerator is actually greater than the degree of the denominator. Therefore, we'll have to use the third case of horizontal asymptotes, which I haven't talked about. So, we can write the numerator as this. The x-intercept will come out to be 1, negative 4, the y-intercept will come out to be 4, and the vertical asymptote will come out as 2. Now for the horizontal asymptote, you've got to perform long division, and the quotient will be the horizontal asymptote, except that we'll now call it the slope asymptote, because it's no longer horizontal, it's a slope now. Alright, so the slope asymptote comes out to be 2x plus 10. Great. Now we will draw the graph, x-intercepts, y-intercept, vertical asymptote, and the horizontal and the slope asymptote, and then draw the graphs. I wonder who put that there. And yeah, so now let's graph f of x is equal to 1 over x squared minus 4 plus 2. X-intercepts. Now the working is this, and the y-intercept is this, the working for that is this. Now the vertical asymptote is x is equal to plus minus 2. We already know how we found that out. X squared minus 4 is equal to 0, x squared is equal to 4, x is equal to plus minus 2. Now the horizontal asymptote is simply 2. Now let's plug those in the graph. That's the x-intercepts, the y-intercepts, and the vertical asymptote, and finally the horizontal asymptote, and then draw the graphs. Notice that the graphs don't intersect the x and y axes at any other points than the x-intercepts and the y-intercepts, as we found out. So that's a way you can just know where to put those graphs, And the topic of rational functions actually goes a lot more deeper than this, like the end-to-end behavior, holes, etc. But maybe that's for another day. Alright, so that's all the functions I could do. It's not all though, but really, can you blame me? But actually you can, but that's not the point. How many functions are left anyway? 4? That's the trigonometric functions, the hyperbolic trigonometric functions, the onto and the into functions. But yeah, that's about it, I guess. If you have any suggestions on how I can improve my videos, then please comment them down below, because yeah, I'm really looking forward to okay, bye.